Hello and welcome to our first video, and chances are you've already read the title. And my name is Dylan, and today we're going to be covering the most essential. All right, well, uh, it's a tie between this and something else that we'll get to later on. Um, Concept of calculus, and that is a derivative. Let's spell that Derivative. And the derivative is something very cool. And we're going to get into some applications and how to calculate that later on. But right now, the objective of this video is just to visualize and understand um, and understand what a derivative really is. And the easiest way to do that, I've found so far, is with this basic definition and looking at some graphs. So we're going to do that real quick. This definition, this is a kind of a abridged or I guess you could say paraphrased definition, but rest assured it is essentially what a derivative is. A derivative, a derivative is a function that yields the slopes of tangent lines to its original function. To its original function. And I know that this can seem kind of crazy because you're like, whoa, hold up a minute. We got two functions in here that are somehow different. We got tangent lines, which are trig. And well, hopefully, I guess if you're taking a calculus class right now, you've taken some sort of trigonometry, and you know what sines and cosines and tangents and secants and everything are, and SOHCAHTOA and all that stuff. But if not, that's fine. I'm gonna be going over all how to do that in these videos. But we got that in here. We got slopes, the good old dreaded M, and yields. That's just a fancy word for provides us with or solves out to. And then we've got the derivative, the golden child of this whole entire sentence. And we think to ourselves, holy moly, that's a lot of stuff. What the heck is that anyway? Well, if the easiest way, like I said, is looking at some graphs. So let's do that. Looking at graphs is fun. Nobody even has to do any math. It's just all visualization. If you can oops, if you can visualize anything, you can understand it, and it's not going to be that difficult. I assure you. It's just a matter of wrapping your head around it. Um, but we have our x-axis and we have our y-axis right here. And let's say that we just took let's do it in red. We just took a function. If you've taken an algebra class, you know that y is the same thing as writing f of x. It's just a different way to write the same thing. But in calculus, almost at every point, unless you're in parametrics and everything, you'll be writing it as f of x. F of x equals x. You know, the good old diagonal line. Let's make that a little bit neater. Let's go ahead and do the good old trace tool. There we go. It's just a straight line, you know. It goes off. It's a ray if it starts from the origin, and it goes off in that direction forever. Or if you're starting everything back, it goes down that way forever as well. But at every single one, it's one on the y-axis right there, and at 2, it's 2 on the y-axis, and at 3, it's 3 on the y-axis, and so on and so forth. And that kind of allows us to think about this and say, all right, well, if it's increasing, rise over run every single time of one rise and one run over, well, we know that our slope here is 1, right? We know that. We can see that. We know that up 1 over 1, up 1 over 1, up 1 over 1, and so on. We can see that. We can understand that, hopefully. And if we think about that already, we say, okay, well, if we know that our slope is 1, and we draw a tangent line, and what a tangent line is a line at any point on a graph that touches only a single point, only touches one point on the graph. Um, that is a tangent line. Um, we could see that this is going to end up being, well, the tangent line is going to be the same exact line because all the slopes are the same. And if all the slopes are the same, well, if we were to put that as a function, changing the slope over time, which is just what a function is, our function's going to be the straight line. And right, it's just going to be a straight line because their slope isn't changing. It's just going to be the same one value over and over and over and over. And if our slope is 1 at that point, well, we can just say that f of x, or f prime of x, we got our f prime of x. That's how you denote a derivative, is you use a little prime symbol right there. Is just the same thing as 1, right? So it's just going to be a straight line across, right? Because every y value is 1 no matter what the x value. So we can see that, right? We understand that. We can visualize that this right here is our derivative. That's our derivative, and that this lovely function right here is our original function, and that this, if we were to plug in the values of this at any point x, we would get the slope of a tangent at any point on this other function. Now, a cool way, this is something really neat that I particularly enjoy, but I'm strange. I like trigonometry. Um, Trigonometry is a, oh gosh, I really hope trigonometry. Yeah, it's correct. Okay, I think. Um, Trigonometry is neat. Trigonometry is neat. We have sines, cosines. So let's compile a little list. Sine, cosine, tangent. This one's cosecant, secant. I always mix these two up. They I don't understand why they did this, but they did. And then we have um, secant, cosecant, cotangent. Secant, cosecant, cotangent, sine, cosine, and tangent. And we get arc, sine, and all these crazy ones, arc, cosine, and arctan. Just awful things. But we can visualize derivatives in a really, really, really neat way using trigonometry. We're gonna do that right now. Let's go ahead and draw our graph out, right? So we've got our x, and we've got our y, and we've got our that's another x. Oops. There we go. We got our y. If we were to say, all right, well, let's put it in this nice screen. Let's see here. We've got our function, and our function is going to be a sine function, okay? So we've got sine of x, and we all, hopefully, at this point in our mathematical careers, know what a sine function looks like. It starts at 0, goes forward a little bit, gets a hump, goes forward a little bit, and so on, and goes and does like that until it never stops, because it goes to infinity. You can see that it actually would go that way and do the same thing in this direction as well. But going forward for this, well, let's take a look at these slopes, okay? Let's take a look at these slopes, and before that, let's go up here real quick again to this definition of using the functions right there, right? These two words are important. It's saying that basically, if if your first function, if your first y formula is a function, it passes the vertical line test, and it is continuous, and it does not have any asymptotes in there, it is going to be able to have a derivative taken from it. And that derivative will also be a function. It's not going to have any asymptotes in there or anything because it cannot contradict this and this have to be the same thing. Not the same thing. I shouldn't say that. They have to be within the same realm of possibility. We can't have something really crazy happening like with this tangent line. It can't be doing that. It can't be doing this or something. Whenever we have just a straight line, that's just not possible. But if we take that knowledge right there and we come down here, we say, all right, well, sine of x is a function because it doesn't it's continuous, and it passes the vertical line test. So we can graph before we even know how to mathematically solve for a derivative. We can graph that using slope by just looking at saying, all right, well, let's do it in orange, or a mix between orange and yellow, mostly yellow. But we can look at this and say, all right, well, the slope here is the tangent line at this point, right? The tangent lines at all the peaks on this original function are 0, which means that our slope for this sine function at that particular point must be 0. And for our graph to represent that slope, we must have a crossing of the x-axis at each 0 point underneath a peak of the sine function. Yeah, does that make sense? We have to have it. We don't know right now if it's going this way or that way or this way or that way or however it's moving, but we know that it's going to have to do that in order to get the 0 slope right there. Um, Next, if we wanted to see actually if it was doing this or however it was going, we would look at positivity and negativity of the original function. So that'll determine the increasing or decreasing of our own derivative. Because let's see here, we're going to try and f prime of x for derivative is going to equal, we don't know yet. We don't know yet, but we want to know. We say, oh, but we know trigonometry, and it's interesting. It's interesting, and I want to know what this is. We can say, look at this. All right, well, we know that it's 0 here. And if we take it and we say, okay, well, if we're looking at positive and negative values, it's safe to say that if something is going from a decreasing or a negative direction or a negative value to a positive direction or value, that we know that our derivative, our slopes, must be changing in a certain way. So if it's going from negative to positive, we know that it's going to have to be increasing, apologies, increasing I'm sorry, not increasing to, just it's going to have an increasing slope. And if it's going from positive to negative, it's going to have a decreasing slope, right? And we can see that. We can see that right here. It's going to, from this point up to here, the slope is going from negative to positive, so therefore it is increasing. But after this point right here, or after this point right here, it stops increasing and begins to decrease, because we can see that right here, the slope right here is much sharper than it is up here, which means that if their slope right here is 1, then maybe here it's 1/2, and then here it's 0, because it can't go from 0 to 0. It has to go from a high value to a low value, because we know these are 0. These slopes right here are 0 at all of our peaks. So we can see that there's a point right here where it switches from an increasing slope to a decreasing slope, and we can plot that. We can plot that. We plot that right here. We know that this is going to be the point right here where it switches from increasing to decreasing. And you can see again here that the same instance is happening here. It's going from a decreasing slope into a more even slope, so it must be increasing, and it's going to not extend past the lowest or highest y values of our functions, because that, again, would contradict what the function would allow. And again, here it's going from increasing to decreasing, which means we have a point here where it's going to slope back down. And then here we have another where a little bit past our axis, I guess you could say, where it goes from increasing to decreasing. So if we were to take it and graph that, we would say, all right, well, let's look at this. Let's look at this right here. If we were to look at this, we would say, okay, well, let's graph this. And it's not going to be pretty, but, we're connecting the dots, doing a little bit of graph stuff. We get to this point right here. We can say, whoa, look at that. I encourage you, if you don't know what this is, to pause it for a minute and really just try and put the pieces together for yourself. And at this point, I'm sure you've done so. You can see that this derivative is actually going to end up just being a cosine function, which is incredibly neat to me, because we can see that these two functions coexist infinitely, and we can assume that if we were to do the same thing and take a derivative of this, we would end up with some variant of a sine function, and if we take another derivative of that sine function, we get another variant of a different cosine function, and that would just go on forever and ever, and that's very interesting. But that about concludes it for this video on what a derivative is. And remember, it's just a derivative is a function that yields the slope of a tangent line to its original function. And we can see that this is true both for this function because our slope was 1, and there's no change in the slope at all across any infinite time period, so we have it going all the way across the x values. And down here, we can see the same thing happening just with the slope of a wave function, like a sine or a cosine. We have the same thing right here. And that has been what is a derivative. And I hope to see you in the next video where we will begin to actually start solving some derivatives.